the Gauss-Seidel method is not the whole story. Actually, here we're going to see what's called the SOR method, which is a slight modification, a slight improvement based on the Gauss-Seidel method. So the SOR method, or, or the successive over relaxation method. So basically, it's the following. It's based on the following. Generally, iterate methods like the Jacobi or the Gauss-Seidel method usually converge to the correct solution from one side. That's the correction from one iteration to the other always stays on the same side of the sign as the number of the iteration increases. So that basically means the following. Let's consider, for example, this is the axis, and we do have that the exact value is this. This is the one. This is the U star is the exact value. And if we start at some point of the iteration, if we start at some value here, just increasing the number of the iteration, you are getting closer and closer and closer to the exact value, but always going from one side. And here, the SOR method is making something, we'll see later, so that starting from one side here, it allows the method to go to the other side, from one iteration to the other, so that going from the next iteration, it can go to the other side, and then goes back to the other side, which might speed up the convergence. So as said here, this is used, moving from one side to the other, by this SOR method to speed up the convergence. And so what is the SOR method doing? So basically, the SOR method in the iteration we have that is calculated in the following way. Is the weighted of the U value obtained in the previous iteration and the one which is obtained by the Gauss-Seidel method. So you are combining the two just using this parameter omega. 1 minus omega times the one obtained in the previous iteration, and omega times the one which is obtained in the iteration by the Gauss-Seidel method. And this omega parameter, which has to lie between 1 and 2, is the one which allows it to go from one side to the other. Because as you can see, if it goes from 1 to 2, as you can see here, it will be negative. So it allows to the U vector to go from one side to the other. Of course, this SOR method can be written in this way. Here you have to choose which is the parameter omega that you want to use, and this parameter has to be between 1 and 2. Of course, if you're using to be 1, it's actually going to be the Gauss-Seidel method. Then, of course, it can be written in order to make it more efficient in a more short way, just using the matrix representation that we have seen before. So, for example, using the matrices, you have that it would be the U vector evaluated at the j plus 1 iteration. This is 1 minus omega times the U vector evaluated at the j iteration. This here we do have its omega times the inverse of the diagonal, which is multiplying. This is the Q vector. This is minus that. This is the product of the triangular matrix times the U vector evaluated at the j plus 1 iteration. And this is minus the lower triangular matrix times the U vector evaluated at the j iteration. So this expression here can be written this way. And what you can do here is, in order to make it shorter and have an expression just for the U vector evaluated at the j plus 1 iteration, which can be considered in the matrix representation in order to apply and to use for the implementation of this method, what we have to do is we can bring this expression, this term here to the other side. Of course, remember that this is multiplied by omega times d minus 1. You bring it to the other side, and then you can clear from here just the expression for the u evaluated at j plus 1 iteration, and the result that you have is this one. This is the result that we do have for the u vector evaluated at j plus 1 iteration in this SOR method. And of course the question might be, but which parameter is the one we're using? We know that has to be between 1 and 2, but which one is the one that we can choose? Is there any optimal parameter that makes the method the fastest one? Of course it is. And actually, there's a way of getting which is the omega parameter which makes the method the fastest one. And just for curiosity, it can be obtained, and I will want to explain just very shortly how can be obtained the optimal choice for this omega parameter. And for this, we can evaluate the error at the iteration j, but the expression we have for the j minus the exact one, even though we don't know which is the exact one. And the rest, just considering the expression, the general expression for this one, for this u vector, you can get actually that the errors are at the iteration j plus 1 in terms of the error at the iteration j. And here is the thing. Considering this expression, okay, the SOR method will converge provided that the largest of the moduli of the eigenvalues, which is called the spectral radius. The spectral radius is the largest of the moduli of the eigenvalues of this SOR matrix, which is this matrix here. So if you calculate the eigenvalues of this matrix, and this is the spectral radius, so it will converge that procedures whenever that spectral radius is lower than 1. If it's lower than 1, it will converge. Otherwise, it will not converge that method. And besides that, so it's given to us a criteria for the convergence of the method. And besides that, there is a theoretical optimum value for omega, and this is the one that makes the spectral radius minimum. So in practice, we can calculate that more easily. So just considering that you can iterate for different values omega and calculate the spectral radius for different omega, so you can get the minimum for this omega. And this is the minimum, this is the omega that we should use in this SOR method in order to have the optimal value, and in order to get with this optimal value to get this iteration procedure with this omega. But otherwise, if you have not obtained this optimum omega, you can use for different omegas and see which is the one that's getting the lowest, the fastest one when applied, when this SOR method it's applied. So again, here what we have seen is a slight optimization of this Gauss-Seidel method, which basically relates that instead of just going from one side, we're just getting closer and closer and closer to the exact one from one side. It allows the method to jump from one side to the other, so with the expectance that the convergence is getting faster.